Okay, so what is a process? So if there is a program on your disk, so let's just say you installed Microsoft Word, and now it's just a program on the disk. It's not doing anything useful. So when you double click on the icon for Microsoft Word, you have a process, a live entity, something which is alive inside your computer. That entity gets resources on your computer, like it contends for CPU time, it gets a chunk of your memory, it can access files on your disks, it can display and things on your monitor, and it can accept things from the keyboard and your mouse or any other input device that you might have. Okay, so a process is a program in execution, as is mentioned over here, right? Um, so the way processes are laid out in memory is something like this. So when you write a program in a high level programming language like C, for example, you need to compile it to object code or machine code, right? So that code is usually present on the disk before you start the program. When you start the program, when a process is created, it is given some area in memory where it can store its things, right? For example, the program that you write and that gets compiled, basically the instructions that are going to execute on the CPU are stored in a section called as the text section. So this is where your code is stored. What is your code? You write programs in C, Java, etc. All of this is converted to object code, and this code basically stays here. Your program can make use of the heap. So if you have ever used the malloc function and you get a pointer, let's just say you get a character pointer uh, called buffer, okay, and this thing is of length, let's just say 1024 bytes. So all of that memory comes from an area of memory called as the heap, okay, and the stack is used for function calls. So let's say you are running in the main function, and inside the main function you make a call to another function. Let's just say it's the add function. So you say sum equal to add 2 comma 3. Okay, so what happens? With the 2 and 3, a new stack frame is created. The 2 and 3 are passed here. If add creates a new variable inside the function, so let's just say the add function begins here, so it can create a thing called int sum, and then later sum equal to whatever the parameters are, a comma b, right? Sum equal to a plus b. So then the local variables like sum inside the add function are created on the stack. The sum, which is 5, will be returned back on the stack so that main can read from it. Let's just say the main function has multiple lines of code, and here you call the add function. So main, when add returns, the main function should not start executing from the beginning again. It should start executing, continue executing from the next line after add. So the return address of this line is also stored on the stack so that the computer can continue executing from the line after add. So this is why the stack is used. It's used for function calls. It needs memory, and the process is a live entity. It will keep making function calls. So it needs the stack. Usually the stack grows downwards in memory in many architectures, and that is fine, from higher memory to lower memory addresses. And the heap grows upwards in memory, that is from lower memory addresses to higher memory addresses. The data section is used to store global variables. What is a global variable? Any variable in C, for example, if it is declared outside the scope of any function. So let's just say before you start your main function, you make a variable called int a. So this A is a global variable. It is available to all functions inside the C file. Okay, and if you declare it as an external variable, then it is also exported. And if you write your program in a fashion in which your code is distributed across multiple C source files, all of them will be able to see A, and that A will have just one location here, but all the code anywhere that mention A will be referring to that one area of memory. So this is a global variable. Local variables are created on the stack. Dynamic memory is given from the heap, and global variables come from the data section. So this is how a process is laid out in memory. Okay, and the processes are called as jobs and batch systems. Batch systems are computers where the jobs or the processes are not interactive. So you give them a job and say, this is how the input looks like, this is what I'm looking for as the output, and this is the algorithm you need to run to convert the input to the output. This will keep running for 2 days. They'll come after 2 days and collect the results. If something is wrong, they'll modify the program or the inputs and then submit another job and come back after 5 days, right? So those are called as batch systems. There is no interactivity. It's not like you enter a command and then immediately the computer gives you the result. So over there, processes are also called as jobs. In time shared systems, what are time shared systems? The computers like ours, where multiple users can be logged in, or even if one user is logged in, they can have more than one process running on the system. And all the processes think as if they have complete access and ownership over the computer, but they don't. A program runs for a few milliseconds, then another program is context switched over that program that runs for a while, then another program, and in a while the first program gets a chance. This happens so fast that you get an illusion as if you are running all the time. Such systems are called as time shared. The time is shared in a sequential manner across processes, and those systems are called as time shared systems. Okay, we have talked about this. A program is a passive entity, processes are live entities or active entities. Once you start a process, it becomes active, and a single program which is on disk can become multiple processes that can run simultaneously. For example, you have your Word program on the disk and there is an icon on the desktop. You double click on this once and you start writing one document. Let's just call that document 1. And then you double click on Word again and you start writing another document, document 2. The program that is stored on the disk is just one program. Okay, this is just one program, but you have two processes running. Two processes. So a single program can manifest itself as more than one processes running simultaneously, and to the operating system, each of these processes are independent of each other. The operating system does not care that these processes have come from the same program. The program is dead. The program is just a file on the hard drive. But when you double click on it multiple times, you can create multiple processes all running simultaneously. Is this idea clear to everybody? Yes or no?
Yes, sir.
Okay,
Yes, sir.
cool. So let's go to the process states. So when a process is being created for the first time, okay, it cannot run immediately. As you might have guessed, there is a lot of groundwork needed for a process to be able to run. One of that is provisioning enough memory for the process so that it can keep its code, data, keep, stack, and different things in memory. Right? And multiple things need to be done. More memory has to be allocated for a bunch of other files that this process wants to read. We will look at memory map files later, shared memory, whatnot. So while all of that is happening, the process is in the new state. It is not eligible to run. Once all of that is over, then it can be admitted into a ready queue. It is a queue inside which it will be admitted. It cannot start running immediately. Why not? Because when it gets admitted into the ready queue, maybe the CPU is running something else. Why should it immediately let this new process run? maybe something more important is running on the CPU. So this process, along with potentially many more processes, will wait in the ready queue. Okay, there is a module inside all operating systems almost, which is called as the scheduler. The scheduler runs algorithms on the ready queue and determines which process should run next. So once this process which is running, stops running for various reasons, as we will see in a minute, then the scheduler chooses another process, ready process from the ready queue, and then puts it into the running state. That means that process is running on the CPU right now. So let's just say our process gets picked up by the scheduler from the ready queue and it is running right now. So what can happen when a process is running? On interactive systems, on time shared systems, should we allow that one process to run for 5 minutes and not let any other process run for 5 minutes? Should we do that?
No, sir.
No? Okay. All right. So this process can do multiple things. Now, there are two kinds of processes. Like we have CPU bound processes and we have input bound processes, input output bound processes. CPU bound processes mostly do compute. Input output bound processes mostly do input output. Like they might want to access the disk very often, or they might want to get input from the keyboard very often, or they might want to do other things like print a document. They're just used for printing maybe, right? So these are all input output tasks. Compute tasks can be, maybe it is training a machine learning model, or it is computing a huge spreadsheet, right? Each of these things are all compute bound processes. So if it is a compute bound process, what can happen is that, well, if you give it all the time in the world, then it can take 10 minutes to finish whatever it was doing. But we cannot let that happen. So as I told you before, and I'm telling you again, the only way to stop the CPU from whatever it is doing right now and have it do something else is to cause an interrupt to the CPU. If the CPU is interrupted, only then it will stop and say, okay, now tell me what to do. If you tell it to do something else, it will start doing that. And then you have to interrupt the CPU again to have it do something else. So now the CPU is running your program. How do we interrupt the CPU? Because this program is not raising a system call. It does not need many services from the operating system. It is not trying to read anything from the disk also. Well, so how do you stop it? Well, there is a very important interrupt in computer systems. It is called as the timer interrupt. Okay, a timer, it runs for a few milliseconds or whatever periodically, and then after every time period it is configured for, it is going to interrupt the CPU and say, okay, I'm interrupting you. So when this timer interrupt happens, right, so what will happen? So let us say the timer interrupt is number 10. So in the interrupt vector table, we will go 0, 10. So the CPU is going to come here, figure out the address, jump to this address. Here we will have operating system code present, and this will handle the timer interrupt. And this code will eventually call the scheduler. Okay, what is the scheduler going to do? It will take your process, it will put it back into the ready queue. You were ready to run. There is no problem with you. Just that the scheduler now wants to run another process, because we have to give every process chance from time to time. We cannot let one process run for a long time. Then the system is going to become unresponsive. Users will not find it easy to run the operating system, and the operating system will not be able to satisfy one of its major goals. Okay. So the process is put into the ready state. Well, it will run again if the scheduler picks it up in a future point of time. But right now the scheduler is going to run, and it is going to pick another process from the ready queue, and it will make that running. Okay, that is one possible path our process can take if it is CPU bound. It is not trying to do any input output. Well, if our process is an input output bound process, so after running on the CPU for a very small amount of time, it might say, I want to read 10 lines from that disk file. Without that, I cannot proceed any further, because I need to read those 10 lines and I need to figure out how many vowels are there in those 10 lines. So without those 10 lines, the program has no point in continuing. So then how is it going to get those 10 lines? Well, it is going to raise a system call. A system call is nothing but a software interrupt, right? And the CPU is going to be interrupted. Operating system code is going to run, and it will see, oh, you need input from the disk. you know what I will do? I will not let you run any further, because this disk input output is going to take way longer time than we can let you sit on the CPU, right? The CPU is very useful, it will run something else. In the meantime, why don't you wait? So the process will go into the waiting state. It is waiting for the input output to happen. So once the input output has happened, the input output will then give its own interrupt. Then again the operating system code will run. Then it will see, oh, this input output was for this process. It will then wake up that process from the waiting state. Then the process will go to the ready state again. Now it is ready to run. It has all those 10 lines from the disk file. And then the scheduler will again run because of the timer interrupt or any other processes calling the system call, or for any reason an interrupt happens, the OS gets a chance to run the scheduler. Okay, and the scheduler will more often than not pick up a new process to run. Okay, that's how it maintains interactivity. It maintains that smoothness. Okay, and then that process will run. So the process, when it is new, it is being created, it is in the new state. Once it is admitted to the ready state, it will wait there until it has been picked by the scheduler. Once it is picked by the scheduler, it will go to the running state. Two things can happen from there. Three things rather. Well, it can run to its finish. It is done with whatever it is doing. Then it can exit and become terminated. Or it does something illegal, like it divides by 0, or it starts accessing memory outside whatever has been allocated to it. Then it can become terminated. The OS is going to kill it. The other thing that can happen is that it is CPU bound, and then it is not going to give control over the CPU by any other means, by interrupting the CPU. So it is running on the CPU doing computation. The timer interrupt will fire and say, okay, now your time is up. You go back to the ready queue. You will be called at a later point of time. Let someone else run for now. Or it can make a system call, ask for input output. Operating system will put that process in the waiting state. And when the input output is done, it will be put back into the ready state. And then it might be picked by the scheduler whenever it feels that is appropriate. Is this clear to everybody?
Yes, sir.
Okay, any questions so far for this? Okay, I'm going to share the recording of this. I mean, I barely got any time. It's like the COVID situation is really, really, really bad. I mean, it's all got all of us really, really scared, right? So I'll have to collect the emails that Google Meet sends me after about 15 minutes after every class, and then I'm gonna send you the videos. It will be useful for you while preparing for exams and for whatever reasons you might want to use it. Just don't put it on YouTube or anything. Don't share it with anybody. Just use it for your educational purposes. That's all. Okay. Sorry? Hello? Okay. All right. So process control block. So just like you guys have an ID card where your name, your parents' name, your whatever, date of birth, maybe your photo, your hostel name, what semester you are in, whatever. A bunch of things are given, your emergency contact number. Similarly, processes also have some kind of an ID card where all the information needed for them to run properly is stored. For example, the state of the process, whether they're in the new state, running state, ready state, terminated, or the waiting state, right? Any 5 of those 5 states can be marked here. Each process has a unique process number, also called as the PID, process identifier. It's a number given to a process so that it is uniquely identifiable on the system. Then every process can store a program counter. Now, what is a program counter? So you will learn more about this in your architecture class, but I'll give you a brief here. So on the CPU executes program after it fetches instructions from the memory. So here is your RAM, and this contains your compiled code. So the CPU fetches instructions and also data. Data can also be written back when instructions are usually read from the RAM. The CPU executes it. So instructions can be multiple instructions. Let's just say the CPU is executing this instruction. There is a special register inside the CPU called as the program counter. The program counter points to the next instruction that the CPU is supposed to execute. So the CPU is executing this instruction. PC will point to the next instruction, so that when the previous instruction is executed, the PC will then help the CPU, because PC has the address of that instruction, right? So then that address will be used to get that instruction from the RAM, and then PC will then increment and then it will point to the next instruction, right? Why do we need to store the program counter in the process control block of this process? Can anyone try to guess this? Why does this need? This is stored in the CPU. Why to store it in memory inside the process control block for the process? Can anyone try to guess it?
To retrieve the data,
To do what?
fetch the data.
Fetch the data. Which data? No, that is happening in the program counter on the CPU. Okay, this process control block is stored in memory. This is not in the CPU. This is just a memory structure. So what can happen is that it is not guaranteed, and then also the CPU also has registers. As I told you before, probably that registers are very fast pieces of memory which store temporary data. So the CPU, as I said, fetches data from the RAM, it stores it in a register. Then it keeps working on that register, like adds, subtracts, multiplies, divides, and or XOR, not, many different operations can be done on registers. And then once you are happy with your operations, then you can store the result that is stored in some register back to memory. And those registers can also be stored in the process control block. Okay, here. So why do we store all these pieces of information? It is because if once a process gets running, it is not guaranteed that in that one shot itself it is going to finish executing. It is not guaranteed. It can get interrupted by the timer. It can make a system call, and then the scheduler can schedule another process and then later come back to this process. So this process will be interrupted before it completes. So when it is interrupted, it is important that the state of the CPU is stored in the process control block, because later when you try to run this process again, this process must continue from where it had left. If it had left at a certain point of time, then it needs to continue from there. It cannot start from the beginning. That is the reason we store these things in the process control block. Is that clear to everybody?
Yes, sir.
Yes, sir.
All right. So many other different things, like as you will see in later chapters, we will talk about scheduling. Like we will talk about priority scheduling. Different processes can be given different priorities, and then whatever is of higher priority will be given a chance to run before processes which have lower priorities. So priorities can be stored. Many different things, like the amount of CPU time used, what all different chunks of memory have been allocated to this process, how many files has this process opened, whether it's for read, write, whatnot, where they are stored, many different things. What are the children of this process? As you will see, not in this class, maybe in the next class, that a process can create children. And so the process IDs of those children will be stored in the parent process. And the process ID of the parent will be stored in the process control block of the children. Okay, it can go both ways. So all of these things are stored in the process control block of a process. Each process gets one process control block. Okay, so now let's see what a context switch is. Okay, let's look at the concept of a context switch. So what's a context switch? So let's just say, and time is flowing in this direction here. Let's just say process P0 is executing right now. Okay, and then we either get a timer interrupt, the periodic interrupt, which helps the operating system keep its interactivity intact and not let one process run for a very, very long time. Either it's that interrupt or a keyboard interrupt or a system call that this process itself has raised because it needs some services from the operating system. All of these things are interrupt under the hood anyway. Okay, so when it is interrupted, what will happen is that this process will stop executing for a while because an interrupt has been raised. The CPU will stop doing whatever it is doing. It will then try to attend to the interrupt. So before doing all of that, the state of this process, before running a lot of code, Because if you run a lot of code, what can happen? You will end up overriding the registers, and we need to store a copy of the registers. Otherwise, where process P0 ended and whatever it was doing, that information might get corrupted or it might get lost. We don't want that. The first thing to do is save the state of process P0 into its own process control block. Okay, so that is stored into its own process control block. After that, the scheduler code, okay, might run, and the scheduler might determine that process P1 should run right now, depending on the output of its algorithm. We will look at all these algorithms very soon. And then what we can do, so the process 1 was probably executing before, so its state, wherever it was stopped, is stored in its own process control block, PCB1. So the state from that, the program counter, the registers, memory information, open files, all of that will be reinstated or restored. And then it can start executing. And after some time, then it can also face a timer interrupt. Or maybe it makes a system call. Then we store its state into its own PCB. The operating system code runs. At the end, it runs the scheduler. And then maybe it decides, okay, P0 should continue executing again. Right? It was idle all this time. Its state is restored, and then that starts executing. So this time and this time, these periods are called as the context switch periods, because here the context of the CPU, the context of the operating system got changed from process P0 running to process P1 running, and in this case from P1 running to P0 running back again. The context got switched. So this process is called as a context switch. Is that clear to all of you what a context switch is?
Yes, sir.
Nice. Okay. So far, is it making sense? Whatever we are learning right now, all of you?
Yes, sir.
Yes.
Yes, sir.
Okay, cool. I'll send the slides up, send the videos to all of you. So there is no need to take notes or anything. You can watch these videos if you want to, or you can read the book if you want to. You can watch YouTube videos. After a while, you know, I kind of have YouTube videos from, I think, memory management and further. These videos are not there. So if I get time sometime to sit down and do all of this again, then I'll put them on YouTube. But right now I'll give you these videos on your email or WhatsApp or whatever. Anyway, so we will get to threads a little later in the next chapter, so no need to worry about this. So the process control block is somehow implemented like this. This is just a small glance into how it looks. This is a glance into how it looks in Linux. This is a very important operating system, like more important than Windows any day. So in Linux, a PCB is an instance of a task struct. It is basically a structure whose name is called as task struct. And if you make an instance of this structure, you will be able to store the contents of a PCB for a process. For example, this has a process ID, PID, it has the state, like running, whatever, waiting, how much time slice is given to this process, right? You will see what time slices are when we look at the round robin scheduling algorithm. There is a pointer to the parent of this process. There is space reserved for the children of this process, different files opened by this process, and the memory information for this process, right? So as you can see, these things are not just bookish. These things exist in the real world. And if you are inclined enough, you can go and figure out how these are implemented in even toy operating systems like XV6, whose code you should be able to easily understand if you know a little bit of C and a little bit of i386 architecture knowledge. If you want, I can share those manuals with you, and you should be able to tinker with the code for XV6. It's a very small operating system, but if you're able to understand that, then you can go ahead and try to understand the source code for bigger operating systems like Linux. I encourage interested students to do that. Okay. Then we have process scheduling. So why do we need process scheduling? So I was talking about the ready queue. Okay. So what is the ready queue? The ready queue is a queue of processes where all the processes are ready to run, right? The scheduler has to pick up one process out of all of those processes and make it run. So how does the scheduler make that choice? Which one to select to run? Well, there are many algorithms for that, but let's look at the different queues involved in the process. Okay, so all the processes in the system are kept in the job queue. Only the ready ones are kept in the ready queue. If a process is waiting for input output on a particular device, then that process will be put on the queue for that device, as we will see in the next slide here. This is the ready queue. What does this say? So looks like PCB 7 is at the front of the queue. That means process P7 is ready to run. Process P2 is also ready to run. This is the ready queue. Now looks like there's a magnetic tape unit 0 and no processes are waiting on it. There is a magnetic tape unit 1, also no one is waiting on it. There is a disk 0 and then 3 processes are waiting on it, 3, 14 and 6. So these processes are all in the waiting state and they are waiting in the queue for the disk. The terminal is also like a monitor or whatever and a keyboard. So looks like process 5 is waiting on the terminal. So these are all device queues and this is the ready queue. The scheduler usually goes to the ready queue and figures out, well, out of 7 or 2, which one it's going to pick up, depending on whatever its algorithm tells it to do. Okay, let's look at this diagram. What is this trying to tell? So looks like once a process gets into the ready queue, it can get picked up by the scheduler and then it will get a chance to run on the CPU. What it can do is if it finishes, then it becomes terminated. Terminated if it is done. Otherwise, it can do one of these things. Maybe it does a system call for input output request. So if it does input output request, it will be put out of the CPU. It will be put into one of the input output queues, like a disk queue or some other kind of a input output device queue, where once the input output is done, it will be brought back from the waiting state. It will go back to the ready queue to be scheduled by the scheduler at a future point of time. Maybe the time slice allocated to it expires. Well, how does it expire? Well, the timer interrupt happens. It tells the CPU that, hey, you need to stop. The time given to this process is over. Okay. And then the time slice expires. It will not go to the waiting state because it is not waiting for anything, right? It is ready to run again. It just has to wait for the next chance for the scheduler to pick it up. So it goes back to the ready queue. If it creates a child, let's just say it creates it, so it becomes a parent and then the child. So the parent and child are two separate processes. Now the slide is a little bit wrong here. The child cannot execute here. Everybody executes on the CPU. No one executes outside the CPU. The only thing that happens outside the CPU is input output because that does not need the CPU. Okay. So both the parent and the child go back to the ready queue. Okay. Here the parent and the child both are sitting in the ready queue. The scheduler can choose any one of them. The child might get selected before the parent or vice versa, and they will execute. Okay. Or it is waiting for an interrupt. What is this interrupt? You might say, Jyoti, you said input output request go through this. Well, longer input output requests like reading from the disk or printing a document will go through this. But if you have run a scanf command, okay, and you are waiting for keyboard input, well, then you are not going to be put in on any IO queue, right? You are just waiting for an interrupt. And when you type something on the keyboard, then well, it will be accepted by the program and then it will go to the ready queue because the keyboard interrupt occurs. The program gets whatever it wants, then it goes back to the ready queue. Is this making a little bit more sense to all of you? I'm just saying the same things again and again. That's all. Like the more these things land on your ears, the more oriented you will become towards these kinds of things. All right. So now, okay, we're doing pretty well today. Okay, so there are 3 kinds of schedulers. Okay, and this is a very important thing. They keep asking this in exams, and this is the medium-term scheduler. So, what is the difference between a short-term, long-term, and a medium-term scheduler? Difference between these 3. It's a very common exam question. But it's easy to answer that if you really understand what it is. You never have to prepare this again in your life, right? So short-term scheduler, or it's called as the CPU scheduler, is the most important scheduler in your system. Sometimes that is the only scheduler present on your system. What is its job? Well, its job is what I have been telling you this entire class. Its job is to look into the ready queue, run a small algorithm, figure out which process to run next, and then put that process into the running state. Then very soon the timer interrupt will fire, or that process will want for input output. Then the scheduler will be invoked again, and then it will figure out the next process to run. So this scheduler is invoked very frequently, okay? And its job is to maintain the interactivity and the time sharedness of the system. So that is basically what the short-term scheduler is. We will look at multiple algorithms that the short-term schedulers employ to be able to figure out the next process to run in the next few classes. Then there is a long-term scheduler. What is the job of the long-term scheduler? Well, this basically decides which processes to even put into the ready queue. Once the processes are in the ready queue, then the short-term scheduler can work on it. But who puts the processes in the ready queue itself? It is the long-term scheduler. So the long-term scheduler does one important thing. It controls the degree of multiprogramming. What is the degree of multiprogramming? The degree of multiprogramming is the number of processes active in the system at any one point of time. Okay, if you have very few processes active, then your CPU might be sitting idle. Your memory resources are probably not being used to their fullest, right? But if you have too many processes active at any one point of time, then, well, the computer will start to hang. You press a key, it will not appear on the screen. It will take a little bit of it. You will see a little bit of delay. It has happened to all of us. So it is the job of the long-term scheduler to kind of control how many processes even get into the ready queue. Also, as I told to you before, we have two kinds of processes: CPU bound and input output bound processes. CPU bound processes do computation, right? For example, they train machine learning models, or they are working on some scientific computations from inside an Excel spreadsheet, right? So they are CPU bound processes. They do very little input output. Mostly they spend their times on the CPU. Input output bound processes, on the contrary, they do input output from disks or graphics adapters, things like that, right? So if a system has mostly input output bound processes, then they will just quickly go to the CPU, and then they will go to the waiting state. So the CPU is going to be idle. You're not using the CPU. But if most processes are CPU bound, then the interactivity will also go away, because whoever is getting on the CPU is taking the complete time slice, right? That is also not good. So the job of the long-term scheduler is to make sure that a good mix of processes, little bit of CPU bound, little bit of IO bound processes, get into the ready queue. So not only does it control the degree of multiprogramming, but it also controls the ratio between input output bound and CPU bound processes. Is this clear to everybody? Hello?
Yes, sir.
Okay. All right. So that's that. So now we will move on to what's a medium term scheduler. So let's just say the long term scheduler did a pretty good job at selecting, let's just say the system can only handle 100 processes at any one point of time. And you made a mistake, or let's just say you thought 20 processes will anyway terminate very soon. So why not put 20 more processes on the ready queue? But those 20 processes you thought will die very soon, let's just say they did not terminate or they did not die. So now your system has 120 processes. Now you are running out of memory. You do not have enough RAM to keep all of these 120 processes. So what can happen? You cannot let the system just crawl to a halt, right? So what the medium term scheduler does is it takes processes completely. It takes the entire memory image of the processes, of those processes, of a few processes, and then it flushes them. It kicks them out to the hard drive and says, you stay there. We cannot run you right now. Okay, your state is stored. You can continue from where you left off, but for the time being, get out from the memory. Then let's just say it brings the degree of multiprogramming to an acceptable level of performance. Then a few processes will start terminating, Then the processes which had been flushed out to disk, they will be brought back and they can execute smoothly. That is the job of the medium term scheduler. So the process of flushing things to the disk and bringing them back is called a swapping. It swaps. It swaps the location of those programs. They were on the RAM running, but not able to run properly because too many processes were there. Some processes were swapped out to disk. When there was more comfortable space in the RAM, then those processes were swapped in. They were swapped out before, now they are swapped in from disk to memory, and they will be able to run comfortably. Is this clear to everybody?
Yes, sir.